Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered how psychologists measure tricky feelings or attitudes that aren't just a simple yes or no? Is there a way to understand things like happiness or stress when people can't just pick a number but have to show it on a sliding scale? Well, this new research dives deep into exactly that. Today, we're exploring a new tool called BoundIRT, an R package that helps researchers analyze data from surveys, where answers aren't just categories like agree or disagree, but are more like a point on a line. Think about those visual analog scales, or VAS, where you mark your spot on a line to show how much you feel something. From not at all to very much. These are common in measuring pain, mood, personality, and lots more. The problem is traditional methods aren't always great at handling this kind of continuous, but always limited data. This paper introduces our package BoundIRT, which aims to fix this. It brings together 4 popular ways to model these tricky bounded continuous responses. Why is this important? Because when researchers use different methods, it is hard to compare results, especially when you want to see which model best fits the data. This package aims to make things simpler, more consistent, and easier to use. Before this package, analyzing this kind of data was a bit scattered. You'd find different ways to model it, some using complex estimation methods. And the tools weren't always user-friendly. For example, researchers might use something called Marginal Maximum Likelihood, or MML, to estimate how well items measure a trait, but without a unified tool. Doing this across different models or comparing how well different models fit the data was a real headache. This inconsistency is a big deal. It makes it tough to choose the right model for a dataset. Plus, getting things like plots of item information or predicted densities, which help us understand how good the survey items are, could be extra work and prone to errors. And crucially, most existing methods stop at just measuring the person and the item parameters. They don't easily let you do the next big step, using those measurements to explain other things. That is where BoundIRT shines. It is designed for the whole process. First, you can fit different bounded continuous ART models to your data. Then you can compare their fit to pick the best one. After that, you can look at plots to check if your items and the whole test are measuring what they're supposed to. And finally, and this is a big one, you can use the package to run regression analyses on the underlying trait you are measuring. This means you can see how that trait relates to other things, like demographics or other behaviors, which is often the ultimate goal of such research. The paper describes 4 main models that BoundIRT can handle. These include the beta IRT model, same-GMA's continuous IRT model, the simplex IRT model, and the normal linear IRT model. Each model has its own way of describing how a person's score on an item relates to their underlying trait, and how spread out the responses are for each item. Now, a tricky part with these models is that they assume responses are strictly between 0 and 1, meaning they don't touch the exact edges. But in the real world, people often do mark the very ends of a scale. The researchers dealt with this by proposing a way to handle these 0 and 1 inflation issues, essentially allowing for a higher chance of responses at the extreme ends. How do they make these models work? They use a powerful statistical technique called Markov Chain Monte Carlo, or MCMC sampling. Think of it as a very thorough and sophisticated way of exploring all the possible values for the model's parameters, like item difficulty and discrimination, and seeing which combination best explains the data. They use a tool called the No-U-Turn Sampler, or NUTS, for this, which is quite advanced for drawing samples from these complex probability distributions. Once the models are estimated, you need to figure out which one is the best fit. BoundIRT offers a few ways to do this. One is by estimating the fully marginalized log likelihood. This is a bit like a superpowered way of calculating how likely the observed data is given the model, and it naturally penalizes overly complex models. They use a technique called bridge sampling to estimate this, which is a clever way to estimate values that are otherwise impossible to calculate directly. Another approach uses information criteria like Lewick and Wake. These are standard tools for comparing models. They essentially balance how well a model fits the data with how complex the model is, helping you choose the most parsimonious but accurate explanation. The package also helps calculate these by marginalizing the likelihood with respect to the person parameter, which is important for these types of latent variable models. And now for the really exciting part, the latent regression. After you found the best measurement model for your data, you can use the trait scores estimated by that model as the outcome in a regression analysis. This is where you can start to answer your bigger research questions. For instance, does a person's level of a certain trait predict their academic success or their reported happiness? BoundIRT provides tools for this two-stage analysis, which correctly accounts for the uncertainty in the estimated trait scores. This is a crucial feature because if you just use the average trait scores, you might underestimate the uncertainty in your overall findings. They use sophisticated corrections, building on work by researchers like Kroon and Vermont, to get more accurate estimates of these regression relationships. To show all this off, the paper walks through an example using data from the abasement scale of the adjective checklist. This scale measures things like feeling anxious, despondent, and submissive. The responses were originally on a 60mm line, and they've been converted to a 0 to 1 scale. The researchers used the BoundIRT package to fit different models, like the beta IRTs and same GMA IRT models. To this data, they use multiple MCMC chains to ensure the results are stable and reliable. They then examine the results looking at things like the item discrimination parameters, or alpha as they call it, which tells you how well an item differentiates between people with different levels of the trait. They also look at the gamma zero parameters, which are related to how much zero inflation there is, meaning how often people choose the absolute lowest score. The summary statistics help them check if the model's estimation process has converged, meaning it has settled on a stable set of answers. They also perform visual checks, like trace plots, which are like a visual diary of the MCMC sampler's journey through the possible parameter values. If the plot looks like a fuzzy, wiggly line without any major jumps or patterns, it suggests the sampler is exploring the space well, which is good news for reliable results. Scrollplot fit beta, what density items 1 to 4 xlab beta IRT replace after fitting the models. They use the plot function to visualize things like the model. Implied densities, which show what the responses to an item are expected to look like according to the model. They can also plot the item characteristic curves, or ICCs, which show the expected response to an item at different levels of the underlying trait. They also look at item information curves, which show how much information an item provides about the trait at different levels. For model fit assessment, they simulate replicated datasets from the fitted models and compare them to the actual data. This is called posterior predictive checking. They use density plots to see if the model's predictions line up with the real data. In this case, they note that while both models capture the main peak of the data distribution, neither perfectly captures a smaller secondary peak. Then, to get a more formal comparison, they use the Bridgebird function to estimate the marginal likelihood. A higher marginal likelihood generally indicates a better fitting model. They calculate a Bayes factor, which is a ratio that tells you how much more likely the data are under one model compared to another. In this specific example, the Bayes factor shows overwhelming evidence for the same GMA ERT model over the beta ERT model. They also calculate Lewick and Wake values, which are information criteria that help select the best model. These values also point to the same GMA ERT model being a better fit for the abasement data. With the best model selected, they move on to the latent regression. They use the Laterbird function to see if a person's gender, in this case represented by the predictor variable, female, relates to their score on the abasement scale. The results show the estimated regression slope. In this particular analysis, the covariate female did not show a significant relationship with the abasement trait score, meaning that based on this data and model, gender didn't predict how someone scored on this measure of self-criticism or submission. So, what is the takeaway? The BoundIRT package is a really valuable tool for researchers working with bounded continuous questionnaire data. It streamlines the process of fitting, comparing, and interpreting complex ERT models. It even allows for advanced latent regression analysis, giving researchers a more complete picture of the underlying traits and how they relate to other factors. The developers are also looking to expand it for multidimensional models, which could be huge for analyzing complex cognitive or psychological constructs. What I find really impressive about this research is the effort to unify and simplify complex statistical modeling. When you have specialized tools that address specific data types, it makes sophisticated analysis accessible to more people. The focus on Bayesian estimation and methods like bridge sampling means researchers can get robust estimates and robust model comparisons, which is crucial for drawing reliable conclusions. One limitation, as hinted at in the paper, is that while they've tackled 0 and 1 inflation, real-world data can be messy. Also, the package currently focuses on unidimensional models, but many psychological constructs are multidimensional. Future work on extending this to multiple dimensions will be really important. For us as consumers of research, this kind of work means findings from personality questionnaires, mood ratings, And other scales measured on continuous formats will be more reliable and easier to interpret. It means we can have more confidence in the reported relationships between traits and outcomes. It is the backbone of better psychological science. What do you think about this approach to analyzing survey data? Let me know in the comments below, and if you found this breakdown helpful. Please give it a thumbs up, subscribe to Rubin's Mind Lab for more science explained simply, and hit that notification bell so you don't miss our next deep dive. Thanks for watching.